Hey, future chemical engineers. Welcome to the classroom. So, in this series, we're going to be covering a couple of topics that will give you a feel for what it's really like to study chemical engineering. Today, we're going to be covering mass and energy balances. So first, what is a balance and why should you care? Well, let me ask you this. Do you care how much money you have in your piggy bank or bank account? Or how much gas you need to put in your car to go on an epic road trip? How about the amount of electricity it costs to heat your food? Well, today we're going to be learning two simple rules that I learned more than 20 years ago when I studied chemical engineering, and I still use today. So, let's start with the most important part. Your money. It's pretty simple, right? Whatever you put in, minus what you take out, is what's left. Easy. Well, congratulations. You just did your first balance. In minus out is accumulated. This can actually be even simpler. If we take out exactly as much as we put in, the amount inside doesn't change. Chemical engineers call this steady state, and we use it all the time. Think of it like a bathtub. If the water flowing into the bathtub is equal to the water flowing out of the bathtub through the drain, the level of water in the bathtub will stay constant. I know, a chemical plant like this one can look pretty complex and intimidating when you first see it. But don't worry, the same idea still applies. If the plant is at steady state, what's flowing in must equal what's flowing out. Chemical engineers call this the rule of conservation of mass. And it states mass is neither created nor destroyed, only transferred from one form to another. I know this sounds complicated, but think of it like Lego blocks. You can start with some Lego blocks and you can take them apart and then build something new. But you can't create a Lego block from thin air or make one vanish. This is exactly the same. Let's look a little bit closer at a piece of equipment that we use often on chemical plants. We call it a burner. And what it does is heats one stream up from one temperature to a higher temperature. And it does this by burning a fuel, like natural gas. Actually, this is very similar to a gas hob or stove that you use to cook your food. For the most part, natural gas is comprised of a compound known as methane. Methane has one carbon atom bonded to 4 hydrogen atoms. When we combust or burn methane, the carbon gets converted into carbon dioxide gas and the hydrogen gets converted into water. But we're missing one critical component here, the oxygen. Usually, we get this oxygen straight from the air around us. Now, using the rule of conservation of mass, we can calculate the exact amount of carbon dioxide and water that we produce for every kilogram of methane that we burn. This is because we can't create or destroy carbon, so every gram of carbon that comes in must leave as carbon dioxide. And every gram of hydrogen that comes in must leave as water. We can do exactly the same for the oxygen, but in this case we have to work backwards. So, if we know how much water or carbon dioxide is created, we can calculate how much oxygen was needed to create those two. The great thing about the rule of conservation of mass is that it works for one unit or the entire chemical plant. So, if the plant is steady, everything flowing in must equal everything flowing out. This is really convenient because it allows us to check whether we're missing any information. So if we add up all the streams flowing in and subtract all the streams flowing out, if the answer isn't 0, we know that something is wrong and we can go look for it to find out what we forgot. Okay, let's go back to the burner. We talked about it heating a stream of material from one temperature to a higher temperature, the same way you heat up your food in order to cook it. The same way that we have the rule of conservation of mass, we also have the rule of conservation of energy. And it says basically the same thing. Energy cannot be created or destroyed, it is just transferred from one form to another. So we can apply this in exactly the same way that we apply the rule of conservation of mass. But in this case, what's happening is that the chemical energy stored in the bonds of the methane between the carbon and the hydrogen are being broken and converted into heat, which we can then use to heat the stream. We can actually calculate this very easily using the ancient mythical technique of thermodynamics. Don't worry, we're not going to go into that today. We'll leave that for another exciting episode. But in short, all we need is the chemical formulas for what we start with and what we end with. So in this case, we can look up the energy for methane and oxygen, and then subtract the energy for carbon dioxide and water. Then we'll know how much energy is released for every kilogram of natural gas or methane that we burn. So in this way, we can accurately estimate the amount of natural gas needed to heat the stream from one temperature to another. We can do exactly the same if we want to know how much gasoline we need for our epic road trip. So in this case, most cars burn gasoline, not methane, but the calculation is very similar because gasoline is essentially also just a mixture of carbon and hydrogen, known as hydrocarbons. Then, in addition, we can calculate the amount of carbon dioxide that we would release during our entire trip. Now, this is very important if we want to control the concentration of carbon dioxide in the atmosphere. Something we'll talk about on another day. Congratulations! You are now a chemical engineer. Well, not quite. But you have learned how to use the rule of conservation of mass and the rule of conservation of energy. This is something that chemical engineers do all the time. So congratulations nonetheless. Now, we have made a lot of assumptions along the way, and this was a simple first introduction. We assumed that the natural gas is pure. We assumed that complete combustion occurs. But don't worry about these details. You'll learn about them later. This is really the key to being a chemical engineer. We take those complex processes and chemical plants and make simplifying assumptions so that we can apply these rules. Now, the tricky bit is knowing which assumptions you can make without making a big mistake. And this is something you'll learn through practice over many, many years. So, if you found this useful, please leave a like so we can discuss more of these interesting topics. Cheers!